Right. I'm going to go through the first 3 assignments for this week. Then I'll create a separate video for assignments for next week later. Okay. So just first, I just want to mention the CER and Galileo. You're just going to read page 40 of your conceptual physics book. I also posted the pictures to that on Google Classroom. And so you can read about it and fill out the CER as it lists on your assignment there. So hopefully CERs at this point are pretty well explained. If you have questions on how to do a CER, just email me or text me on Remind or something. Hopefully it's pretty self-explanatory there. You obviously won't have any scientific evidence in this case. It's mostly just kind of like more like an essay you would write for like English class. But it is good to know about Galileo. He is really important to how all this stuff works. And now I'm just going to go to part 2A there. So it says figure 3.8 on page 48 of your textbook. And if you look there, it shows somebody throwing a ball up and then watching it come back down again. Now the figure is actually comparing the velocities of the ball. By the way, because we all had to do the same work as the other classes, one of the classes has already read the book, this chapter, so I would recommend reading it on your own to get a better idea of what we're talking about here. It does go along with what we've already been talking about, but it might be a better way to understand it might be reading for you, so I would try reading it. But you can see in the picture, as the ball goes up and down, the velocities are the same, just in opposite directions. So the speeds are the same, but the velocities are different in that they're going in opposite directions. But that's really important to how gravity works, really. So you can see if he throws the ball up, it's going to come down at the same exact speed, just coming down instead of up. But we want to actually figure out the velocity and the distance for each time the ball is in the air. So there's these 2 equations that I give you that are kind of complicated. I've already put my table here. I'm only going to do the first 4 seconds. You can do the rest yourself. That's pretty self-explanatory, hopefully, at that point. But let's go through the first couple together. So the first equation here is velocity. So something that we didn't really get to talk about in class is just velocity is equal to, velocity is just equal to distance divided by time. Okay. So the farther something moves in a shorter amount of time, the faster it's moving, which makes sense. Now there's another equation that I don't believe they give you in the book here, but oh yeah, they do. The instantaneous velocity of an object falling from rest. So it talks about it for free fall on page 46. So if you read page 46, it has a better understanding there. Also, page 45 has some information on acceleration versus velocity. So velocity is also acceleration times time. Now when something is falling, this acceleration is little g, meaning gravity, okay? It's the acceleration due to gravity. So that is why ultimately the equation that they give you for this that I give you for this problem is velocity is equal to v sub 0, or v0, which is the initial velocity of the ball being thrown up, and minus g, which g is going to be the acceleration due to gravity, which is 10 meters per second. It's actually 9.8, but we're just going to round up to 10 to make things easier, times the time that the ball is in the air. All right, so I'm just going to do a couple of these, and then hopefully you can do the rest yourself. So let's figure the velocity for 0 seconds. So velocity is equal to the initial velocity we wrote down there is 20 meters per second. I think in the book it has it as 30, but we're going to use 20 here because that's what I wrote down there. Yeah, so in the picture it's 30, but we're going to use 20. So 20 meters per second minus 10 meters per second squared. Now that squared there just means acceleration. and just means it's an acceleration number, so I'm not actually squaring any numbers, times the first one is 0 seconds. So if I just plugged in my calculator, 20, this 10 times 0 is 0, so 20 minus 0 is 20, which makes sense. At the very beginning, the ball is going at 20 meters per second. So I would go up here and I would write 20 meters per second. Okay, now I'm going to do the same thing. It's still initially at 20 meters per second. 10 is always going to be the same because its gravity is always the same everywhere on Earth. And then the time, though, is 1 second. So after 1 second, how fast is the ball going? Well, 10 times 1 is 10. 20 minus 10 is 10 meters per second. So after 1 second, the ball is going at 10 meters per second. So I'd go over here and I'd write 10 meters per second in the box there. Okay, I'll do a couple more. So it starts at 20 meters per second, as always. The initial velocity is always going to be 20. Gravity is always 10. But now we want to know at 2 seconds how fast is it going. Well, 10 times 2 is 20. 20 minus 20 is 0. So at this point, the ball is going 0 meters per second. So at this point, the ball is at the top of its arc right there, right before it's going to fall down again, okay? So we have 0 meters per second. You could probably already see the pattern here, but let's go ahead and do a couple here. So the last one that I'm going to do, or no, I'm going to do 2 more. Times 3 seconds. 20 minus 30 is negative 10 meters per second. So now it starts going downwards at 10 meters per second. So if you look at the picture, that would be near the top, right? In this case, it's after 4 seconds. For us, it only took 3 seconds for it to start going downwards now at 10 meters per second. Okay, and then if you do the math again, you'll get negative 20 meters per second here, and you can do the rest yourself and see where we get to. Okay, we would have to do this over a cliff like they did to see what's happening. All right. Now I'm going to erase this part, and now we're going to talk about how distance works in this case. So I'm going to erase all this, and let's talk about distance. So now distance, as it says, is, if you look at the book, it actually tells you distance is 1/2 gravity times time squared. But in this case, we have an initial velocity, which means the distance is also caused by the velocity. If you remember, velocity was distance over time. Well, if you multiply both sides by time, that reduces out, and what you're left with is distance is equal to velocity times time. So if we multiply the velocity by the time, we get how far something is traveling. But then in this case, we also have to include the distance due to the acceleration, how the acceleration is changing it, which is where we get that 1/2 1/2 GT squared. We're not going to derive that whole thing, but that's the equation we're going to be using. This is the initial velocity and minus 1/2 GT squared. All right, so we're just going to plug in some numbers again. So the distance is going to be equal to, so we have 20 meters per second is the initial velocity. The first one we're going to do here is for 0 seconds. So we're going to add in 0 seconds there. Minus 1/2 10 meters per second squared is the gravity's acceleration. And then 0 seconds squared. Well, if you look, 20 times 0 is 0. That's 0. 0 squared is 0 times anything is 0. So ultimately what we're left with is 0 meters, which makes sense. At the very beginning, it hasn't gone anywhere yet. So it starts with 0 meters for distance. All right. Now, after 1 second, let's see how far it has traveled. So notice initial velocity and gravity are the same, but now we have 1 second in for the time. All right, so 20 times 1 is 20. 1 squared is 1. 1 times 10 is 10, times 1/2 is 5, 20 minus 5 is 15 meters. So after 1 second, the ball has gone 15 meters up into the air. Okay. Oops. Next one. 2 seconds. So now we replace the t with 2 seconds. Okay, so we might have to get my calculator here. Okay, 20 times 2 is 40. 2 squared is 4 times 10 times 1/2. And so 40 minus 20 is 20 meters. All right, so the ball has gone 20 meters of distance after 2 seconds. Now, okay, well actually let's do another one here. So same speed, initial speed. Now we have 3 seconds. Same acceleration, but now we have 3 seconds squared. All right. So 3 seconds squared is 9 times 10 is 90 times 1/2 is 45. 20 times 3 is 60. So 60 minus 45 is 15 meters. Okay, let's do the last one here. 4 seconds. Four squared is 16 times 10 is 160 times 1/2 is 80. 20 times 4 is 80. 80 minus 80 is 0 meters. All right. And then if you do the next one, you'll start to see negative numbers. So for the next one, you'll get, I believe, what would that be, negative 20 maybe? 5 squared, 25 times 10 is 250, times 1/2 is 125, 20 times 5 is 100, so you get negative 25 meters. So when you start to see negative distances, that means it's going below the person, right? So if you look at the picture, the ball first goes pretty high, it goes 15 meters, and then it goes 20 meters, so see how it goes from the first second, it goes from 0 to 15, it jumps 15, and then from 1 to 2, it only jumps 5, from 15 to 20. That's because the ball is slowing down, and 20 is the peak. So this is the peak of the throw, and then it starts coming back down again, right? Down to 15, back down to 0 where the guy is after 4 seconds. And then it starts getting negative. That's because it goes below the ground level, right? So this only works on a cliff, because if you didn't have it, it would just hit the ground, right, and stop. But if you're on a cliff, it can start to go below you. So that's what those are trying to show you there. Okay, so that would be the table, the first table for 2A. Okay, so that's filling out the whole table there. Now 2B, it asks you to fill out the table for just somebody dropping, just dropping a ball instead of throwing it up again. Okay, now I'm just gonna erase these, and so you should create a new table. Create a new table, just like this one, except now we're gonna use slightly different equations. All right, so now we're dropping the ball instead of throwing it up into the air. Now, because we're just dropping the ball, it doesn't have an initial velocity. So our velocity is just going to be due to the acceleration, which is g times t, gravity times time. Now this case, we're dropping it down. The initial velocity is 0, and instead of a negative, we're just going to say downwards is positive in this case. So everything going downwards is going to be positive instead of negative. So before, upwards is positive. Now this time, downwards is positive, okay? Okay, that's for the velocity. So let's go ahead and plug in some numbers again. So the velocity, g is still 10. So 10 meters per second squared is the gravity's acceleration. The time is, we're going to start with 0 seconds. Well, that's just going to be 0 meters per second. Okay. Now we're going to do 1 second. 10 times 1 is 10 meters per second. Okay, now remember all this is happening downwards, so it's going 10 meters per second down, which before we labeled it as negative 10. Now we're going to call it positive 10. We're just flipping which direction we call positive. Okay, totally legal to do in physics, as long as we label it. Okay, 10 times 2 is 20 meters per second downwards. Okay. 3 seconds is 30 meters per second, and I'll just go ahead and do 4 as well. Is 40 meters per second. So we have 30 and 40. Okay, now the rest you're going to fill out on yourself. So 5, 6, and 7 you can do by yourself. You can even do an 8th one. I don't know why the top one has 5. Oh, it's because it accidentally skips 6. That's why. Sorry for the mistake. So just do 7 seconds for the first one, and don't skip 6, or go ahead and just add an 8th one for the bottom one. Okay, sorry for that mistake. All right, so you can compare your numbers now and see what was happening. So the first time you saw that the ball had to go up, slow down, and then speed up downwards. That's why the numbers were slightly different. In this case, it's just falling, so it's just going to speed up downwards. It's going to get faster and faster and faster. All right, now, okay. So now we're going to do distance instead. So here, notice downwards is still positive for our distances. And it gives us, now we're going to use that equation that they give us, 1/2 gt squared. So notice, just because there's no initial velocity, we're getting rid of the v0, and we're left with just the 1/2 gt squared. Downwards now is positive, okay? So instead of before where upwards is positive, now downwards is positive again. All right, so the first one, I'll just call it distance. G is 10 meters per second squared, as always. Time, we're going to start with 0 seconds. Well, that's just going to be 0 meters. Okay. Now let's go ahead and do it for the rest of them. So 10 is always going to be G. Now we have 1 second. Okay, 1 squared is 1 times 10 divided by 2 is 5. Wow, that's a bad 5, sorry. 5 meters. Let's do it for 2 seconds. 2 squared is 4 times 10 is 40 divided by 2 is 20 meters. Okay, I'll do it for 3 seconds. 3 squared is 9. 9 times 10 is 90. Divided by 2 is 45 meters. Okay, and I'll finish up with doing 4 seconds. You're going to go on and do 5, 6, 7, and maybe 8 as well. 16, 160 divided by 2 is 80 meters. Okay, so I gotta write those in. So we have 5 meters, 25 meters, 45 meters, and then 80 meters. Now notice, if you look here, the jump from this one to this one was 5. The jump from this one to this one is 20. And then, and then, did I do this right? That's what I did wrong, I'm sorry. This is 20, not 25. All right, so let's talk about this again. So 0, that jumps 5, and then it jumps 15, and then 25, and then, what was that, 35. So you can see as it goes, it's getting farther and farther every second, which makes sense because it's speeding up faster and faster. And so it will continue to speed up forever until it hits the ground again. Or, as we're going to talk about later, it balances out with air resistance. And we'll talk about that's called the free fall velocity or terminal velocity. Okay, so things actually reach a limit on Earth. In outer space, they could speed up forever until they hit the speed of light. All right, so that is part 2B. And now 2C, it just writes, what are you learning as you look at these charts? What are the differences? What are similarities? How does velocity and distance change over time? Probably 3 sentences at least, writing out what is kind of what you're learning as you look at these two charts. All right, now the last thing we're going to do is these problems. So this is the third assignment. Question 2, 4, 8, 10, 12, 16, 18, 20, 30, 32, 34, 36, 38, and 40 on pages 52 and 53. So I'm going to go to 52 and 53 here. So some of them require just kind of writing out your answer, or some of them require you doing some math. So we'll do both of those together right now, and we'll talk through them. So first one is number 2. It says, what 2 units of measurement are necessary for describing speed? So if we're describing how fast something's going, we need to know how far it is divided by how much time it took, right? Distance divided by time. So the 2 measurements we need are distance and time. And that will allow us to describe how fast something is going. Miles per hour, meters per second, kilometers per hour, whatever we want to say. Okay, question number, not 3, 4. What is the average speed in kilometers per hour of a horse that gallops a distance of 15 kilometers in a time of 30 minutes? All right, so we have a couple problems here. So we want to know the speed, velocity in kilometers per hour. Okay. If you recall, velocity is just distance divided by time. So we can do the distance of 15 kilometers divided by 30 minutes. Well, 30 minutes is 1/2 of an hour, right? We could actually do it, so 30 minutes, there is, in 1 hour, there is 60 minutes, okay? So 30 divided by 60 is 0.5 hours, okay? That's called stoichiometry or dimensional analysis. You probably did in chemistry. So 15 divided by 0.5 is equal to 30 kilometers per hour. So that is how fast, on average, a horse is galloping, okay? If they go 15 kilometers in 30 minutes. Now, at some points, it might be going faster. Some points, it might be going slower. But on average, it's going 30 kilometers per hour. Okay, question number 8. If a car is moving at 90 kilometers per hour and it rounds a corner also at 90 kilometers an hour, does it maintain a constant speed or a constant velocity? Defend your answers. So if it's going around a corner, so let's say the car is going around a corner, okay? it starts at 90 kilometers per hour and it's moving this way. But now if it's going around a corner, it's also going 90 kilometers per hour, but you can see that its direction is changing. Well, velocity is just speed with a direction, right? So speed is how fast something's going. Velocity is speed in a certain direction. So, as they're going around the corner, does how fast they're going stay the same? Yes. So speed stays the same because right, they're going the same. They're going the same speed. They're moving this. How fast they're going is the same. So speed stays the same, but velocity must be changing because their direction is changing. Right, so if direction changes, velocity is also changing. Okay, so they're trying to trick you there. Velocity must change if the direction changes. All right, question number 10. What is the acceleration of a car that maintains a constant velocity of 100 kilometers an hour for 10 seconds? Why do some of your classmates who correctly answered the preceding question get this question wrong? So the preceding question is asking the acceleration of a car moving along a straight road that increases its speed from 0 to 100 in 10 seconds. So if the car is already going 100 kilometers per hour but doesn't change its speed at all, or its velocity at all, what's the acceleration? Well, the acceleration is 0 because the speed is not changing, or because the velocity is not changing. If velocity doesn't change, there is no acceleration. Okay, question number 12. Acceleration is generally defined as the time rate of change of velocity. What can it be defined as the time? When can it be defined as the time rate of change of speed? Okay, so acceleration is how velocity changes. Okay, the time rate of change of velocity. Well, if we go back and look at our definition of velocity, velocity is speed with a direction. So acceleration can change, or there can be acceleration only if speed or direction changes, right? Because as long as velocity is changing, acceleration is happening. So acceleration happens if speed or direction changes. So how could we say that how can we say there's acceleration is just if speed is changing? What must stay the same if we want to define acceleration as speeding up or slowing down, okay? So I'm going to let you think that through. Okay, so if acceleration of the speed or direction changes, then how do we define acceleration as only speed changing? What must stay the same in order for that to be true? Okay. Okay, question number 16. What is the gain in speed per second for a freely falling object? Okay, so how much speed is gained every second for a falling object? Well, we just did that on the last problem, right? We actually did a falling object every second. How much was the speed changing? Well, if you look between each one, that's 10, 10, 10, 10, right? So every time we go a second, we're increasing 10 meters per second every second, which makes sense because G is equal to 10 meters per second, or meters per second squared. So because of gravity, something gains 10 meters per second every second, okay? So velocity gained 10 meters per second every second. That's where that squared comes in. So it's 10 meters per second squared. Every second you're gaining 10 meters per second. Okay, so that's really important to notice. That's what that means, acceleration here. So make sure you're understanding that. All right, let's move on. Question number 18. The acceleration of free fall is about 10 meters per second squared, as we just talked about. Why does the second unit appear twice? We just explained that in the last problem. So why is there a second squared? It's because we're gaining meters per second every second. So it comes down to this idea here. Okay, so explain that in words, that it's meters per second every second. Okay, explain that in words. Don't just draw that. I need you to write it out in words as we just explained. Okay, question number 20. What relationship between distance traveled and time did Galileo discover for freely falling objects released from rest? Okay, so if we go back to what Galileo determined, let me find it. So if you look back at page 45, it says acceleration on Galileo's inclined planes. Sorry, we want to talk about free fall, which is, page 48, where it says how far. So Galileo determined that distance is uniformly accelerated object travels is proportional to the square of the time. So he is the one who determined that d equals 1/2 acceleration times time times time. Okay, so you need to write that out for question 20. That would be the top of page 48, where you can find the answer to that one. All right, question number 30. Okay, by the way, we're skipping these thing and do. It's pretty cool. You can actually see that reaction time really determines, we can determine that by, we can determine reaction time by catching a ruler like that or looking at a dollar bill. I think most people can't catch a dollar bill like that, so you should try it on your own. But let's go to question 30 where it says plug and chug. Okay, plug meaning you're plugging the number into the equation and then chugging through by calculating the equation. Okay, so number 30 says calculate your average walking speed when you step 1 meter in 0.5 seconds. Okay, so we just did this before. So average speed is just the total distance divided by the time. Okay, so average speed, which we can just call v, like velocity, is distance divided by time, which in this case is 1 meter in 0.5 seconds. 1 divided by 0.5 is 2 meters per second. So that's your average walking speed. Okay, question number 32. Show that the acceleration of a hamster is 5 meters per second squared when it increases velocity from rest to 10 meters per second in 2 seconds. Okay. And then it gives you that equation, which is not all that helpful. So acceleration, if we look back into our book, acceleration, well, velocity acquired is acceleration times time. Okay, velocity is equal to acceleration times time. So if the velocity goes from 0 to 10 meters per second in 2 seconds, you can see that the acceleration is 5 meters per second. Here's how we can do it. If we divide this by t and this by t, so in algebra we can divide both sides by the same variable. That variable is going to reduce to 1 on that side. And so what we have is v divided by t is equal to a. So acceleration is just the change in velocity over time. So we know that we just did that the velocity change was 10 meters per second, and it took 2 seconds for time. 10 divided by 2 is 5 meters per second squared. That's the per second meters per second. And that's where that squared comes from, just like problem number 18, okay? So you can see that that's where you get the 5 meters per second squared from. Just rearranging that acceleration equation. All right, question number 34. Show that a freely falling rock drops a distance of 45 meters when it falls from rest for 3 seconds. This goes back to our table from the before, okay? So we actually did this calculation right here. So if you look back, we're just going to plug it back into the equation like we did right there, okay? So we're just going to plug it into the 1/2 gt squared equation, knowing that g is always 10 meters per second squared, and that after 3 seconds, we're just going to plug it in and show it's 45. So no matter what, every object is going to fall 45 meters in that amount of time. You, a ball, pretty much anything, okay, on Earth. So you're going to do that for question number 34. I'm not going to do it again. You can do it using that same equation we did before. Make sure you're listing it out. Okay, question number 36. Think and solve, mathematical application. All right, so this one's going to be much longer with many more parts. A ball is tossed with enough speed straight up so that it is in the air for several seconds, just like we did for part 2A. What is the velocity of the ball when it reaches its highest point? So if someone is going to throw a ball in the air, and it's going to come back down, how fast is it moving at the very top of its tallest point? Okay, how fast is it moving? Hopefully you can kind of think that through. Okay, I'm not going to let you know, but we also did this before. Okay, so that's part A. Part B, it says, what is its velocity 1 second before it reaches its highest point? We also did this before, so it doesn't matter. It's always going to have the same velocity. So if you go back and look at part 2A again, you can see the second before it reaches that highest point, what is its velocity, okay? Remember that it's losing, as it goes up, it's losing 10 meters per second every second, okay? So you can figure out how fast it's moving based upon that idea. Again, it's losing 10 meters per second every second. So 1 second before it reaches that highest point, how fast is it going? C, what is the change in its velocity during this 1 second interval? Again, we just talked about it. It's losing 10 meters per second every second, okay, based upon gravity. Okay, part D, what is its velocity 1 second after it reaches its highest point? Again, we did this for part 2A, so you can look back at that. It's after it reaches the highest point, it's now going to fall and gain 10 meters per second downwards, or negative 10 meters per second every second. So after 1 second, how fast is it going from the very top? Okay, E, what is the change in velocity during this time? Again, it's gaining 10 meters per second every second. Okay, and then F, what is the change in velocity during the 2 second interval? Okay, it says careful, so it's trying to trick you. Instead of 1 second, how fast is it changing during 2 seconds, okay? You can look back at the equation in problem 32 to figure out, if you can't think through it, how fast is the velocity change in 2 seconds, okay? And then G, what is the acceleration of the ball during any of these time intervals and the moment the ball has 0 velocity? So gravity never changes. It is always the same on Earth. Depends on where you go, but on Earth it's always the same. Okay, so gravity is always acting downwards, and the acceleration due to that gravity is always going to be 10 meters per second squared. Okay, so don't ever let that fool you. It's always going to be the same. All right, and then let's go to, so even at the very top, it's still accelerating downwards at 10 meters per second squared. It's kind of weird when it reaches the top, but that's always happening. Okay, question number 38. A car takes 10 seconds to go from v equals 0 meters per second to v equals 25 meters per second at constant acceleration. If you wish to find the distance traveled using the equation d equals 1/2 at squared, what value should you use for a? So it's asking for what is the acceleration. Okay, so what is the acceleration of the car? The time it takes, it said was 10 seconds. And the velocity is changing. We use a little arrow, a triangle like this to say change from 25 meters per second to 25 meters per second from 0 meters per second. So the velocity change is 25 meters per second. So we're going to use this equation to find it. We remember before we divided by t for those to reduce out. So we have a is equal to v divided by t. And so we can just do 25 meters per second. It's a change in the velocity divided by 10 seconds. And we can see that it's 2.5 meters per second squared. That is the acceleration of the car. All right, last problem here. Problem number 40. A dart leaves the barrel of a blowgun at a speed v. The length of the blowgun barrel is L. Assuming that the acceleration of the dart in the barrel is uniform. So it's accelerating at a constant rate, just like gravity. Show that the dart moves inside the barrel for a time of 2L over V. And then if the dart's exit speed is 15 meters per second and the length of the blowgun is 1.4 meters, show that the time the dart is in the barrel is 0.19 seconds. All right, so it tells us that there's a speed V. It gives us the distance is L. That's how far it's traveling. And acceleration is constant. And it's looking for the time that it's happening. Okay, but it's accelerating. Okay. Now it's important to know that the speed at the very beginning of the barrel is 0. So we have, let's draw our barrel here. Okay, so at the beginning, so let's say this is the gun part. I don't know how to draw a gun. Okay, so at the beginning, velocity is 0, but at the end, it's v. Okay, so instead of numbers, they're just giving you letters. Okay, that's what's so confusing. The barrel is L long, so we could say maybe it's like 20 inches or something, or 20 centimeters long. Okay, but we're just going to call it L. And we're looking for, how do we know the time is 2L over V? To be honest, I haven't tried this problem yet, so we're going to do it together here the way I would think about it, and let's see if that helps, okay? So the acceleration, well, the distance, we have these equations. Let's write them down. We have distance is 1/2 acceleration times time squared, okay? And then we have velocity is equal to acceleration times time, okay? Does that help us at all? So let's see, we know D is L, so we're going to do some substitution, I think, here. So let's see if that will work. So we already talked about the fact that if we divide by T, we get A is equal to V divided by T. So let's try plugging that in, okay? So we know A is going to be the change in velocity from 0 to V over the certain amount of time, okay? So I'm going to plug that into the first problem. So we know D is L. We know A is V over T. And we have T squared. Well, this is also equal to, if we just multiply both sides, or we just multiply the t in there, this also works. Well, t squared over t is just t. So this is equal to 1/2 v t. Okay, so that's because this squared cancels out with that t there. Just like x squared over x is x, that's the same thing happening here. So now if you look, we can multiply both sides by, well, let's just rewrite it again. So L is equal to 1/2 VT. So again, let me explain that again. I plugged this equation in for A there, okay? So instead of A, I just wrote VT, and that's what I put in the bottom over here, okay? So I just plug it into that equation. Okay, so I'm going to multiply both sides by 2. What that does is reduces that 2 with that 2. And so now I have 2L is equal to V times T. Now I'm going to divide by V from both sides. Those V's reduce out. I'm left with 2L over V is equal, let me rewrite that, that's ugly. 2L divided by V is equal to T, which is what they were looking for. That's part A. Okay, so that's part A, where they're looking for how to prove that the time is 2L over V. We just shown that. Okay, now part B asks, if the dart's exit speed is 15 meters per second and the length of the blowgun is 1.4 meters, show that the time the dart is in the barrel is 0.19. We're just going to use this equation. So time, we're trying to show that it equals, so let's just put a question mark there. We're trying to show that it equals 0.19, so let's see if we're right. The exit velocity, V, is 15 meters per second. The length is 1.4 meters. So time is equal to 2 times 1.4 meters divided by 15 meters per second. If we plug in those numbers, t should equal 0.19 seconds, and therefore we have proven that t is 0.19 based upon that. All right, that problem is much more difficult than the rest. If you didn't quite follow that, that's all right. That is getting into kind of more intense physics, even like AP physics territory, so don't worry too much about that. But that is how you do it. So if you were able to follow it, great. If you do have any questions about any of the other ones, please let me know. So this isn't due till 2 Sundays from now, but as soon as you're done, just take a picture and send it in. That way I can give you credit for it and you don't lose it or anything like that, okay? Let me know if you have any other questions.